First thing I'm going to do is, within most of these things, since it's the cube root of 1/7, that means it's the cube root of 1 or the cube root of 7. Okay. Now, when I split that up, what's the cube root of 1? 1. So I'm not going to worry about that. Yesterday, I made mention that it is always, always, always easier to work with fractional exponents than it is nth roots. So I'm going to change this from the cube root of 7 to 7 to the 3rd. The reason that I do that is because now I can easily see how many more thirds I need to make a whole. How many do you need? 2. So I multiply the top and the bottom to rationalize this by 7 to the 2/3. Remember, I'm keeping the same bases here. The bases don't go away, they don't disappear. And I get 7 to the 2/3 over 7 as that result. All right. That's what that looks like. 48 is very, very similar to that. 48, you have a 4th root, so that means the exponent for both the numerator and denominator wind up being a 1/4. Right away, before I do anything, I noticed that I cannot simplify 80 and 9. Sometimes you might be able to simplify the fractions right off the bat. There's a problem that we did. It's kind of in the, what was it? It had like a 6, a 4. Sarah, what was that one? Was it 26 we looked at earlier, or was it 24? The 6, 4, and the 3? You know which one I'm talking about? You asked me earlier this morning?
34.
It was 30. That one, they all had different bases, but their exponents were the same. So that was like they're all encompassed within the same nth root, so you could simplify before you take care of the exponent now. Here, there's really nothing you can do except for rationalize. Okay? When I do that, how many more fourths do I need to get to the whole? 3 of them. So I have to multiply top and bottom by 9 to the 3/4. Denominator is now a 9, exponent of 1. Okay, so that's good. And the numerator is just going to be 80 to the 1/4 times 9 to the 3/4. And you're done. All it needs to look like. You have nothing left to do. Okay? Why is it? Okay. Correct. Correct. What was the other one? Since you saw the people go over their hands there. Okay. This one is mirroring the idea of this. 2 different bases that have been raised to the same exponent. What they did here is they started you with this. Since that exponent is the same distributed in both parts, you can theoretically undistribute it and get 4 times 64 to the 4th. Double 64, what do you get? Double that. There you go. There's 4 times 64, 256. 256, and we're doing a 4th root of it. Remember, when you take a 4th root, that means you're taking the square root twice. It's nice and convenient that you have a 256, because what's the square root of 256? 16, and what's the square root of that? There's your answer. Like I was saying, you guys got to know, you should really, really make sure you know your squares up through a 20. Really need to know those. Okay. What was the other one now? Yes, sir.
54.
Excuse me. So at first glance here, there's really nothing you can do because the bases aren't the same. But after that, you start to think of, okay, is there a possible way that I can get a cube root out of 81? Well, 81 is 3 times what? 27. So I know that this is going to be cube root of 27 times the cube root of 3. So I get 3 cube root 3 for that simplifying. Take a guess what you can take out of a 375.
125.
And how many of those do you get to the 375? 3 of them. So here you have the cube root of 125 times the cube root of 3. And what is the cube root of 125? 5. I appreciate the enthusiasm though. Now, do they have the same roots? So this is real tough now. 5 plus 3.
29.
There's more.
All right, I know this is really, really tough. I know we can do this together. So, hold this up in the air. 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 Hold this over here and hold it up in the air. How many pieces of paper are in the air? Hold it up in the air. I can put it up. 5. So, hold this up in the air. Hold this up in the air. Hold this up in the air. Now, how many pieces of paper are up in the air? 11. I hate you. It's whatever Peter says, right? Yeah. That's what that looks like. Remember, sometimes the roots themselves, when you're trying to do some combination things, guys, they're gonna hide perfect cubes, things like that. But again, it boils back down to, 81 is 3 to the 4th. It's 3 squared times 3 squared. Okay. 375, gee, it ends in a 5. Take a guess what goes into it. 5. Okay. So you start thinking, okay, can 125 go into it? All right. Those are the things that you're looking for. You got to understand numerical place value and how number sense works. Okay. That's how this stuff goes. There's no other way around it. All right. Excuse me. What else we got? What do you got? Okay. And you said 44? 44. In this case here, again, what I want to do is, I know that I have the same nth, the nth root, which means I'll also have the same fractional exponent. So I can kind of theoretically say that this is the exact same problem, right? So what's 18 times 15? Well, what is it, 270? Okay. So you have 270 to the 1/3.
That's perfect.
I wonder what the perfect cube root is hiding within that. Way to go! So you get 3 cube root 10 when you're done with that. Always try to simplify. Yes, it is. Yes, it is. Okay. 24, 22, 32. That's close. I'd get there eventually. I've had a ton of questions on this one. Yeah. I've had a ton of questions on this one. In this case, if you're playing war on it, it doesn't even really matter because you've got a negative exponent in the denominator. As soon as you have a negative exponent in the denominator, you move it up. Now, remember, the 12s are just the base values, okay? They're the same A value for your base. So you move up to 3/8, you're going to wind up with 12 to the 10/8 times 12 to the 3/8, which means you have same base multiplying what you do with the exponents. So you just add up your exponents. You wind up with 12 to the 13/8. And then I stop for a second and try to figure out, well, the denominator of my exponent is an 8, which means, can I get a perfect 8th root out of a 12th? No. So I'm done. Okay? Yes, sir?
But you also could do, multiplying this 12 10 and 12 negative.
If you're adding the negative 3/8 to it, you would have
like,
yes, and then we get you the same thing. Yep. It will get you the exact same thing. What's up? Yeah. That's it. Stop overthinking it. Gee, that never happens. It's okay. Yes, sir. Nope. This is all non-calculator stuff, guys. This is all non-calculator. All right, good question. I just want to say, what happens if this base did have a perfect 8th root to it? Well, first of all, it would be a lot bigger than 12. It would probably be, let's see, 2 to the 5th is 32. So 2 to the 6th, 64. 2 to the 7th is 128. 2 to the 8th would be 256. That would be the I wouldn't do anything larger than 2's to that power to see how things would come and break themselves out. All right. If you do 1, because otherwise, I mean, you get into, if you think about 3 to the 8th, well, 3 to the 4th is 81. So you'd have to do 81 times 81. At least you don't end up wrong. But the numbers get to be way too big for what we need to worry about. Okay. And that's how a lot of the exponent stuff works. It just gets so large so fast. Okay. But that's a good question. What else? Wait, who else have one? I never deal with the relevancies. Chairs go up, so I remember. I always forget. Hi! How are you? Did you have a good day yesterday? Good. If the denominator, remember, just play war. If it's bigger in the denominator, the numerator moves down. That's it. Same rules apply. The only thing is that, what was the question on here? There was one of them that I was helping somebody with where the denominator was smaller. Was it 38? It was 38, wasn't it? Wasn't that what I was helping you? I was helping you guys with? Okay. Take a look at 38 real quick. 38 is one of those, oops. Yeah, 26 and 38. I'll do both of those here because I want to show you guys there's a little. So, going into 38, guys, whenever I'm dealing with these, automatically rewrite them as fractional exponents. It makes your life so much easier. So as I'm writing the problem down, I would automatically just be writing, it's 7 to the 1/2 divided by 7 to the 1/5. I know right off the bat that 1/2 is bigger than 1/5. But in order to play war, I have to get common denominator. The common denominator between a 2 and a 5 is going to be a what? 10. So I will rewrite that real quick, and I'll get 7 to the 5/10 over 7 to the 2/10. You okay with that? Now, we knew right away that I had to play war. The denominator was going to move up, so it's no big deal. Your final answer was 7 to the 3/10. Correct? All right. The difference between that one and, it was 26, right?
Yeah.
And 26, it was 7 to the 1/5, 3/5. So 7 to the 1/5 over 7 to the 3/5. There's two ways of going about doing this. I'm assuming that most of you guys played war right away and moved the 1/5 down. What'd you do? Okay. So if you move that 1/5 down, what became of your numerator? 1, good. So you had 1 to the 2/5. I'm sorry, 1 over 7 to the 2/5, excuse me. Then what did you do with that 7 to the 2/5 in the denominator? You had to rationalize and bring it back up, okay? That's one method of doing this. So this would be, you knew that you would play war, you'd get 1 over 7 to the 2/5, and then always, no fractional exponents are allowed within denominators, just like we couldn't have square roots in denominators, same idea. You rationalize and multiply top and bottom by the 7 to the 3/5. And you wound up with 7 to the 3/5 over 7. We okay with that? Now, the other method that you could have done that, move this up here, rewrite it. The other way that you could have done this, so it's 7 to the 1/5, 7 to the 3/5. In this example, this will show up from time to time here when we get some more variable stuff in about 5 minutes. When you don't have a whole in the denominator, everybody agree that 3/5 isn't the whole? Good. How many more fifths do you need to make the whole? 2 of them, okay? So if I multiply top and bottom by 7 to the 2/5, do I automatically have the whole now?
Yeah.
Not the H-O-L-E.
I was like, right.
Same methodology, it works the same. It just depends upon how you see it, okay? It's one of those little trick things that if you don't have a whole value in the denominator, you go this route, all right? Sarah?
I think that, yeah.
Mm-hmm. So you 1/5 to the 2/5, so you got this. Well, that's wrong, because play war, you always subtract to the larger.
I think 5.
Because then you got negative up top, then you had to bring it back down, then do all that other stuff. Guys. Oh, I'm on. What's that? Guys. Huh? The what? Yeah, playing war. Okay. Same thing would have happened if this was x to the 5th over x to the 8th. Who wins? All right, so what's 5 or 8 minus 5? What goes in the numerator? Same thing? Exact same thing. Okay. Let's look at variables. Real fast, don't write any of this out. What happens when we get to variables, when we did numerical stuff, we always had we ran across the possibility of doing plus or minus values. When you had nth roots that were even nth roots and stuff that were to the 4th, like to even powers, you could get 2 different values for those things. When we deal with exponents in terms of variables, you will always hear me say, treat them as all variables are positive. A lot of times in instructions, in textbooks, on the CUDA sheets, worksheets, whatever stuff that I have, you always want to just assume that you don't have to worry about plus minuses when we're simplifying with variables. Not like we had to do a lot of it here, but just a little FYI. So here's where things start to get a little interesting. Now we start bringing it in with variables and numbers. And as we go through these things before, when we dealt with simplifying in the past, whether it were fractional simplifying, when we did monomial simplifying, things of that nature, We always dealt with numbers first, and then we worked our way into the variables. So when you think of this one, you've got a monomial underneath the cube root, which means you had to take the cube root of the 125 and the cube root of the y to the 6th. Well, cube root of 125 is hopefully relatively easy. What is that? 5. Okay. So we break that down, we have 5. Now I'm just going to rewrite this for a second. Cube root of y to the 6th. What I want you guys to think of here is, how many times does 3 go into 6? Are there any leftovers?
No.
What's the cube root of y to the 6th?
Oh my gosh, that. Oh my.
Because I wanted to show you that before I showed you the long method. If I rewrote this as a fractional exponent, what do you get for the denominator? 3 is the denominator because it's the nth root, so it's y.
Wow.
Okay. You go through a lot of quick division here. All right. Let's do another easy one. What's that?
Is this supposed to be a confidence based thing? So like, I'm like, okay, I can do it. And then
Yes.
you hit me with like
Yes.
hard stuff.
Yes. Merry Christmas. It's Christmas in July or January. Again, 4th root of x to the 4th over y to the 8th. Well, you just have to take the 4th root of both the numerator and the denominator. What's the 4th root of x to the 4th? X, just 1x, right? What's the 4th root of y to the 8th? So this is x over y squared. And you're done. Okay. Yep. Yep. Remember, your nth root, if you rewrite this, you rewrite these things, your nth root is always the denominator. The exponent is the numerator. All right? Okay, let's do a couple different ones. Now, this is what? 9u squared b to the 10th, all to the 1/2 power. Which means you have to distribute the power. This is a power-to-power problem. It's a power-to-power problem that goes within a monomial. So that means each individual piece has to be raised to the 1/2 power. What's 9 to the 1/2? 3. What's u squared to the 1/2? What's v to the 10th to the 1/2? I know. I just pulled some stuff out of the book real quick as I was putting this stuff together. Remember that it uses x's and y's and all through there. Okay. Me? I love it. You guys are like, oh no, we're screwed. Like, oh no, we're screwed. Okay. Now, start putting it all together into more fractional value. You have multiple variables, multiple exponents, as well as numerical value. Now, we always go through these things, the same rules will always apply. No fractional exponents in the denominator and no negative exponents. Okay. What do you mean the whole thing? Just the z. Whoa, hold on. You're getting ahead of yourself here. I see where you're going, okay? So, my suggestion, when we have stuff that start going into things like this, always start with numbers first, okay? Always start with numbers first, and then move things around accordingly if you need to. So I'm just going to put a fraction bar, and I take care of my numbers. What's 6 divided by 2? 3. Okay. I have an x, and I have an x to the 1/3. Who wins? The x. So, what is the new x? Exponent becomes the numerator. Too many values and things of x there. It was 2/3. So you have x to the 2/3 up here. Y to the 1/2. Is there any other y's in the problem? Nope. So it stays where it's at. And then I go to the z value. Z to the -5. What happens to it? Did I need to worry about the denominator at all then? No. I can erase that if I'd like, or I can put a 1 underneath it. It does not matter. Okay. Let's try another one of these. Fifth root of 5, a to the 5th, b to the 9th, c to the 13th. Let's do that shortcut of the division. Okay. Let's see if we can figure this out again. So, excuse me. Is there a perfect fifth root that goes into 5? No. So I can't simplify the fifth root of 5, can I? Nope. So I'm going to keep the fifth root symbol here and the 5 on the inside and see what happens. What is now the fifth root of a to the 5th? A. So an a comes out. There's nothing left over to stay in. How many times is 5 going to 9? 1 comes out. How many are left? 4. 1 comes out. 4 are left. How many times is 5 going to 13? Twice. 2 come out. How many stay in?
Oh my gosh. Wait a second. Why is that?
Think of it as squares. When you had the square root, bless you. If you had the square root of x to the 5th, x to the 5th can be rewritten as the square root of x squared times the square root of x squared times the square root of x. Do you agree with me on that? What's the square root of x squared? X. What's the square root of x squared? So you have x times the square root of x. Well, what's x times x? 2x. Not 2x, x squared. So again, think of it this way. What's the nth root out here that you don't see? 2. How many times does 2 go into 5? Twice, with how many left over?
That's crazy.
Okay. You guys are all going, what just happened? You're simplifying pairs of nth roots. You're pulling out nth roots this way. So think about it. The fifth root of something means it has to be something to that fifth power. So a to the 5th is a perfect fifth root. The fifth root of jump to the 5th is jump. The fifth root of b to the 9th, well, 9 is b to the 5th, b to the 4th. The fifth root of b to the 5th is 1b. What's left over? 4. Okay? You're pulling out the perfect cubes, the perfect squares, the perfect fifths, sixths, whatever. Okay? It's weird-ish, all right? Okay? Let's go to another one with rationalizing. I want to show you how this works when you have to do it with different exponents. Excuse me. So before I go too far into this one, I want to rewrite this as fractional exponent, okay? So I get x to the 3rd over y to the 7/3. We okay with that?
X to the 1/3.
Oh, I'm sorry. Thank you. I meant to. I think I said the third, but I meant like I wrote 3 instead of the third. So sorry. Now in that denominator, isn't that y to the 7/3? Isn't that more than 1? All right. What is it? How many times does 3 go into 7? 2, and how many are left over? All right. So that means this is y squared y to the 1/3. So you're gonna go with that? Because now I rationalize to get the next whole. How many more thirds do I need to make another whole? 2/3. So I multiply top and bottom, and I move this out of the way here. So 1/3 plus 2/3 is how much? 1. Y squared times y to the first becomes now y to the third. And my numerator is x to the third times y to the 2/3. That's how you eliminate when you have larger than 1 as a fractional exponent in the denominator. You split it into basically what we did there was we made a mixed number. The mixed number where the whole number went with one of the variables, the fractional amount with the other part of it. And then we rationalize off that. That's one of the few times that converting things into a mixed number makes a little bit of sense. Okay? That's the weirdish one. Okay? So far so good-ish?
Yeah.
Okay? No. This is easy. Where's the other one here? Okay?
That doesn't apply.
Yeah, I was going to ask you, anything to the 0 power? It's on this sheet that I've given you guys here. So, real quick, this is number 14. My version, I'm just going to write it out, it's easier. Alright, that looks like a lot of fun. So, I figured to rip the Band-Aid off and give you the problem you guys all been waiting for. Okay. Now, I know this is why you were. That's why, there's always one kid in the class who will actually say it. Everybody else is like in the back of their mind going, I know it's going to get real here pretty soon. So, what's the one thing you don't have to worry about right away? X to the 0. Okay. X to the 0 is what? 1. 1. So I'm just in my head. I'm just gonna make that. I know that's a 1. In this whole gargantuan, awesome-looking problem, is there any coefficient? Are there any coefficients? No. So I don't have to worry about numbers. So before I do anything else, then I'm going to make all of my exponents positive. I'm going to move everything that's negative to become positive, and then I'm going to group them, all the x's in the numerator next to each other, all the y's and so on, put them all in the same basic area so that way I know what to do as my next step. Okay? So I did not have any x's in the denominator that needed to move up. I have a y. I have two values of the y that need to move up, and two values of the z that have to go up, and one value of the z that has to go down. So I'm just going to rewrite my x values first. X to the 1/3, x to the 7/4. And as I'm doing this, I'm going to cross them off so I know I didn't miss one. Okay. Now I'm going to move my y. I already have a y to the half up top. Took care of it. My other y to the half goes up. My other y squared goes up. I have a z to the 4th and a z squared goes up, and a z to the 3rd goes down. All of this fun stuff is still to the 3/2. So far, so good?
We're missing.
Oh, z to the 4th. Thank you. 4/3. Thank you. That still goes here. Okay.
Okay. All right.
Wait just 1 second.
I'm waiting. You're going to want to probably do this on separate sheets of paper because you're going to need more space than the allotted on the sheet that I gave you. Work with your y values in the numerator. What's 1/2 plus 1/2 plus 2? 3. Okay, so far so good. I took care of these guys. In the numerator, I have 1/4 and 2. Now, before I do that, though, can I just do this and make this a 1? There's no reason. You could combine them, but if you start to see you've got whole numbers somewhere, start simplifying out as you go. So now, in my numerator, I have a z to the 4th. I'm just going to leave it at that for now. 1/3 and 7/4. Again, common denominator is going to be a 12. So this is going to be 4/12 and a 21/12. Okay. So that gives me x to the 25/12. Okay. And then the last one would be, what would that be? 3/7, I think?
Yeah.
All of this to the 3/2. Okay. 1 plus 4/3.
Oh, 0.
Okay. Now you have two options. You can try to simplify them before you do the exponent, or take care of the exponent and then simplify. There's really no rhyme or reason which way is going to be easier than another. It just depends on how you want to go. I would probably just distribute my exponent and then take care of everything after that. So let's see, that would be 3/2 times 3 for the y value gives me y to the 9/2. 3/2 times 1/4 becomes 3/8. Three halves, that becomes 20, this goes to a 4, 25/8. And then times 3/2 again becomes 7/2.
Oh, wow.
Okay. Now, within this one, you have the denominators, both are top-heavy fractions. Okay, see that? Okay. So what we did earlier is we split them into their mixed number-ish thingy. How many times 8 go to 25? 3, and how many are left? 1. So this is the same thing, the denominator here is x cubed, x to the 1/8. Same thing here, this is z cubed, z 1/2. The reason why I'm doing it this way is because now I could play my war game a little bit cleaner. I can move things around a little bit more. Yes, sir.
But if there's not X, if there's not an X on the top, you don't have to do that.
You still have to rationalize it.
Oh.
And this is helping to rationalize it through. I know I'm going to run out of time on this one. Finish this one and try as many of the evens of this sheet as you can. Okay? The front side is a lot easier than the back side, I'll tell you that. Okay? I know we're going to run out of time, so we'll finish this one. What I'll do is I'll take this one and I'll finish it up on the window. So if you're back here later on, you can take a picture of it because I don't think we'll get to be able to finish the other part out either. Okay? I guess any of the evens on this one as you can, and we'll go from there. Let's finish that. This. What page is this? There's only 2 more steps, but it's okay.